You've probably wondered, right? How can a physicist look at something totally chaotic, like a tumbling baseball bat, and predict its path just as easily as, say, a simple tossed ball? It feels like it should be impossible. Well, today, we're going to pull back the curtain on the physics they use to tame that chaos. It's like a secret cheat code for motion.
Okay, so look at this. On one side, you've got a simple ball toss. Super simple, right? It makes that clean, predictable arc, a parabola, that you probably remember from a high school physics class. But then, look at the baseball bat. I mean, every single part of it is doing its own complicated loopy dance. It's a total mess. How in the world do you even start to describe that with math?
So that's really the big question we're tackling. How does physics deal with that kind of complexity? Well, it turns out there's a trick, a really elegant cheat code, if you will, that cuts right through the noise and simplifies everything. And the crazy part? It's been hiding in plain sight this whole time. And that cheat code is the center of mass. Seriously, this one concept is so powerful. It's what lets us find the beautiful simplicity that's buried inside even the most complicated-looking movements.
Okay, so here's the secret. This is the magic part. If you just completely ignore the wobbling, tumbling ends of the bat, and instead you track just one special point on it, the center of mass, look what happens. It moves in a perfect, simple parabola, just like the ball did. All that chaos we saw, it's just the rest of the bat spinning around this one single point that's flying smoothly through the air.
So what exactly is this magic point? Well, the formal definition is pretty cool. The center of mass is a unique point that behaves as if two things were true. First, it's like all the object's mass, every single atom, is squished down into that one tiny spot. And second, it's as if all the outside forces, like gravity, are pushing or pulling on that one spot alone. It's what lets us take a whole complicated thing like a bat or even a person and just treat it like a single, simple dot.
All right, let's look at the math behind this. The easiest way to think about it is like a seesaw. If you have just two particles, the center of mass is literally their balance point. The formula you see here is just a weighted average of where they are. So if one particle is heavier, the balance point, scoots closer to it. And if they weigh the same, the center of mass is smack dab in the middle. It's that intuitive.
Now, we can take that simple idea and blow it up to handle any number of particles in full 3D space. I know, that formula might look a little intimidating with all the symbols, but trust me, the idea is exactly the same. We're just taking the position of every single particle, weighing it by how much mass it has, adding all those up, and then dividing by the total mass to find the overall average position. It's still just a weighted average, but now with vectors for 3D.
Okay, but what about a real solid object, like that baseball bat? You can't just count the particles one by one. And that's where calculus comes in to save the day. See, an integral is basically just a superpowered way of adding things up for a continuous object. We're imagining slicing the bat into an infinite number of teeny tiny little bits of mass, which we call dm. And then we do our same weighted average trick on all of them. This gives us the exact center of mass for any solid shape you can imagine.
But here's the good news. You don't always have to fire up the calculus. A lot of the time, we can use a really clever shortcut, symmetry. I mean, think about it. For a perfectly uniform sphere, where else would the center of mass be but right in the geometric center? For a cone, you know it's got to be somewhere on that central line running from the tip to the base. Even for something weirdly shaped like a banana, if it has a plane of symmetry, the center of mass has to lie on that plane. This can save you a ton of calculation.
All right, so we've figured out how to find the center of mass. But the really big question is, what makes it move the way it does? And the answer to that leads us to one of the deepest, most powerful ideas in all of physics.
It turns out the center of mass follows its very own version of Newton's famous second law. F equals ma, right? Well, for a whole system, the net external force equals the total mass times the acceleration of the center of mass. And the key word there, the one you absolutely have to remember, is external. This means that forces happening inside the system, parts pushing and pulling on each other, they don't matter at all for the motion of the center of mass. Only outside forces count.
And this example just illustrates that perfectly. Think about a firework. It's launched and it flies in that nice parabolic arc because of gravity, an external force. Then, boom, it explodes. There are huge violent forces pushing all the pieces apart, right? But all those explosion forces are internal. They're just the pieces of the firework pushing on each other. And so while the individual pieces fly off in every direction, the center of mass of that whole cloud of debris just keeps right on cruising along that original parabolic path, completely unbothered, as if the explosion never even happened. Here's a really beautiful, almost artistic application of this. During a leap, a ballet dancer's center of mass has to follow a parabola.
Gravity says so. There's no way around it. But by raising her arms and legs as she jumps, she can actually shift her center of mass higher up on her body relative to her torso. So what's the result? The center of mass follows its arc, but her torso travels in an almost perfectly flat horizontal line. It creates this stunning illusion that she's just floating across the stage. It's physics as performance art.
Okay, to go even deeper and really understand why this all works, we need to start speaking the language that Isaac Newton himself preferred. And that brings us to our next huge concept, linear momentum.
So linear momentum, which we write as the letter P, is actually pretty straightforward. It's just an object's mass multiplied by its velocity. A good way to think of it is mass in motion, or oomph. A big, heavy truck moving slowly can have just as much momentum as a tiny baseball moving super fast. And here's a key detail. Because velocity has a direction, momentum does too. It's a vector. Now, for a whole system of particles, the total momentum, we use a capital P for that, is just what you'd expect. You add up the individual momentum vectors of all the pieces. And here, right here, is where it all comes together. That total momentum of the entire messy system is exactly equal to the total mass of the system times the velocity of that one special point we've been talking about, the center of mass. This is what makes the center of mass so unbelievably useful. It lets us describe the momentum of a whole complicated system with just one simple vector.
And this connection allows us to rewrite Newton's second law in the way he originally thought about it, which is actually a more fundamental and powerful version. It says that the net external force on a system is equal to the rate of change of its total momentum. Put simply, forces are the things that change momentum. No net force, no change in momentum. It's as simple as that.
Okay, so forces change momentum. Got it. But what about those really short, really intense interactions, like a bat hitting a ball? For those situations, physicists have a special tool called impulse.
Just look at this picture. It's incredible. For that tiny, tiny fraction of a second, when the bat and ball are touching, a huge force is acting on that ball, and it totally reverses its direction and its momentum. Impulse is the concept we use to get a handle on exactly what's happening in that moment.
You can think of impulse as having two sides, like a coin. It's cause and effect. On the effect side, impulse is just the change in an object's momentum. That's the result. On the cause side, it's the force multiplied by how long that force acts. The impulse momentum theorem is what connects these two sides. It tells us that if you want a big change in momentum, you need either a really big force or you need to apply a smaller force for a longer time.
So a cool way to visualize this is on a graph of force versus time. During a real collision, the force isn't constant, right? It spikes up and then drops back down, creating a curve. Well, the impulse is simply the total area underneath that curve. Now, calculating the area of a weird curve can be tricky, so to make life easier, we often talk about the average force. That gives us a nice simple rectangle that has the exact same area, which means it represents the exact same impulse.
All right, we've put all the pieces on the board. We've talked about center of mass, momentum, and impulse. Now we're ready for the big one. This is one of the most fundamental, unshakable laws in all of physics. This is the real superpower, the conservation of linear momentum.
So, let's go back to that new version of Newton's law we just learned. The net external force is the rate of change of momentum. So let me ask you a simple question. What has to be true if that net external force is zero?
Well, if the force is zero, then the rate of change of momentum has to be zero too. And if something isn't changing, well, it's constant. And that's it. That is the law of conservation of linear momentum. For any system that's closed and isolated, meaning no external forces are messing with it, its total momentum cannot change. Before, during, and after any interaction, the total momentum stays the same. Period.
Now, this conservation law is true for any collision in an isolated system, but we can put collisions into two main buckets. You have inelastic collisions. Those are the messy ones. Think of a car crash, where kinetic energy gets transformed into crumpled metal, sound, and heat. Then you have elastic collisions. These are the perfectly bouncy ones, like when two billiard balls collide. In that ideal case, not only is momentum conserved, but kinetic energy is too.
The most extreme version of an inelastic collision is what we call a perfectly inelastic one. This is just a fancy way of saying the objects stick together after they hit. Imagine throwing two lumps of clay at each other so they become one big lump. Because they stick together, solving for their final velocity is actually super easy. You just say the total momentum before the crash equals the total momentum of the new combined object after the crash.
The ballistic pendulum is a classic physics problem, and it's awesome because it forces you to use two different conservation laws. It's a two-part story. Part 1 is the collision. A bullet slams into a block and gets stuck. That's a perfectly inelastic collision. It happens so fast that we can ignore outside forces like gravity during the impact itself. So for that moment, we use conservation of momentum to figure out how fast the block plus bullet is moving right after the hit. Part 2 is the swing. Now the block swings upwards. For this part of the motion, we use conservation of energy to connect its speed at the bottom to the height it reaches at the top. It's all about knowing which tool to use and when.
And for those bouncy, elastic collisions, especially when one thing hits another thing that was just sitting there, you get some really cool and intuitive outcomes. If two things with the same mass collide, think billiard balls. Bam! They just swap velocities. The first one stops dead, and the second one takes off at the first one's speed. If a little thing hits a massive wall, it just bounces right back. And if a huge truck hits a tiny little car from behind, the car gets launched forward at almost twice the speed the truck was going. It all comes right out of the math. Okay, but so far we've been assuming the mass of our system stays the same. What happens when it doesn't? And the ultimate example of a system with varying mass is, of course, a rocket, which is constantly getting lighter and lighter as it shoots its fuel out the back. So how does a rocket even move in the vacuum of space where there's nothing to push off of? Well, it pushes off itself. It works by throwing its own mass, the hot exhaust gas, out the back at an incredible speed. By conservation of momentum, if you throw momentum backwards, you have to gain an equal amount of momentum forwards. The force that pushes the rocket, its thrust, depends on just two things: how much fuel you're burning every second and how fast you're spitting it out. That's the force that makes the rocket accelerate. If you take that idea and use a little calculus, you get the legendary Tsiolkovsky rocket equation. It tells you exactly how much your rocket speed will change. It's delta V. And it all boils down to two key factors: the speed of your exhaust and the logarithm of your mass ratio, which is basically just how much of your rocket's initial weight was fuel versus how much is left at the end. This equation is the fundamental reason why rockets have stages, to dump the dead weight of empty fuel tanks and make that mass ratio as big as possible.
So let's just recap the powerful problem-solving toolkit we've just put together. Step 1, isolate your system. Draw a mental box around what you're studying. Step 2, find the center of mass. Pinpoint that one special spot that represents the whole system's motion. And step 3, follow the momentum. If there are no net external forces acting on your system, then the motion of that center of mass is simple. Its velocity won't change no matter how much chaos and complexity is happening inside your box.
And that leaves us with one last, kind of mind-bending thought to chew on. If we apply this logic to the biggest system of all, the entire universe, then it must be a closed, isolated system, right? Which means its total momentum must be conserved. So what does that tell us about the motion of the center of mass of, well, of everything? Is it just sitting still? Is it moving at a constant velocity? And if it is moving, what in the world is it moving relative to? Something to think about.